says recording, and just as a backup, I'm going to use my one that I know that works. Start recording. There it goes. And let's see, we're going to have to start sharing here. There it is. All right. I'll wait for this to come up. All right. Come on, new whiteboard. There it goes. All right, so what are we doing in chapter 5? Chapter 5 is about energy. It's about thermodynamics. It's about moving energy around. Okay, so the first thing that we need to do is we need to say, well, what is energy? It's the ability to do work or move heat. That's what energy is. Energy, you can do some sort of work. The energy contained in the gasoline in the tank of your car is able to make the car go. And so there's energy contained in the molecules of gasoline, and it can get things going. Okay, so that's energy. Now, there are two kinds of energy in this world, and there is kinetic, which is motion, and then there's potential, which is stored. All right. Now, motion is generally, you can say that it's 1/2 the mass times the velocity squared is equal to the energy. All right, that's energy of motion. And energy stored, there's all sorts, all kinds. And one of the most important kinds of potential energy is electrostatic, and that's energy is some constant called the Coulombic constant, or coulombs. It's Q1 over Q1 Q2 over the distance times a constant. Okay, and this one is going to be very important later on. Kind of store this aside because you're going to need this. This is important later on. Whoops. Phone's ringing. Let me turn that off. Okay. So this one's going to be important later on. So file this away. This one, not so much. Now, kinetic motion, 1/2 mass times velocity squared, is important in the sense of, if anything's moving, it's got energy that's associated with it. But what I mean by not so much for us is, from a chemistry standpoint, we don't really care so much about it. If you go on to physics 1, physics 2, it will be important. All right. So we kind of split out the responsibility as far as what kind of equations we're going to end up doing. Okay. So we have these two kinds of energy here. Now, energy, now I said energy, and I just kind of threw out that term, but energy, we have units for that, okay? And so the units for energy, we have something called the joule, okay? And the joule is defined in terms of SI units. It's not important that we know where it comes from. A joule is basically how much energy it takes to accelerate 2 kilograms of mass 1 meter per second per second. Okay, that's what it is. But a joule is a measure of energy. And we're going to call this letter J. That's what we're going to use. Uppercase letter J. Now, there's an older unit called the calorie. It's defined in terms of water. Okay, now the joule's defined in terms of SI units, kilograms and meters and acceleration. But a calorie is the amount of energy to raise 1 1 gram of water by 1 degree Celsius. So if you have 1 gram of water and you put a Bunsen burner underneath it and you change the temperature by 1 degree Celsius, you just added a calorie. And usually we abbreviate this lowercase c a l, and that's usually what we use. Okay, and oftentimes with joules and calories, we don't generally deal with individual joules many times, and we don't deal with individual calories a lot of times because they're very small. Is often you will see kilojoules and kilocalories, and a kilojoule is equal to 1,000 joules, and a kilocalorie is equal to 1,000 calories. All right. Kilocalories you see a lot of times in food calories. If you look on the back of a package of food and you see, let's see, I was just looking at a can of Vienna sausages this morning and looking at it because I can't eat it. So therefore I just stare at it lovingly because I can't, because I'm trying to lose weight. And worst thing you can do is eat processed food like Vienna sausages, but they're there. And it's 160 calories per can of Vienna sausage, a little bitty thing about this big, and 160 calories on the back of the container. But that's actually, when we're talking about food, that's not a calorie, that's actually a kcal. And we say that's big C calories. But we don't worry about big C, little c. If we're talking about food calories, we generally are talking about kilocalories. So a can of Vienna sausages, it says 160 calories. Understand it's not a calorie, which is the amount of energy to raise 1 gram of water by 1 degree Celsius. It's actually the amount of water to raise 1 kilogram of water by 1 degree Celsius is what it is. All right. And so the relationship between a joule and a calorie is you have exactly 4.184 joules equals a calorie. So while a calorie is the amount of energy to raise 1 gram of water by 1 degree Celsius, it's actually not. It's actually been finessed a little bit to where we say it is exactly 4.184 joules equals a calorie. Now, why is that important? If you're doing significant figures and you're trying to go between calories and joules and calories, keep in mind, since it's exact 4.184, then that won't count for significant figures. The other parts of whatever you're trying to calculate will count for significant figures, but the conversion between joules and calories will not. Okay? So that's energy. Here's our definitions for energy. We have joules, calories, and then we have a relationship between joules and calories. There you go. Okay, now, one thing that's going to be important as we do these things, and it's also going to be important on, on at least a couple of the labs, is the idea between the system versus surroundings. And we have to keep these straight. Okay, system versus surroundings. What is what and where are they? Okay, the system is the part that we're interested in. And this is usually the chemical reaction. Usually. All right, it's usually the chemical reaction. But we have to be very careful about what we say is the system versus surroundings. So the system is also the part we're interested. It's the part that's doing whatever it's doing. Doing something. Usually that's also the system. All right, and the surroundings is everything else, or the universe, if you want to get down to it. Now, system versus surroundings. So how do we tell them apart? Well, it's like this. It's you got to decide what's happening. And so let's take an example here. So let's react sodium hydroxide with HCl to make, what do they make? You have an acid with a base, and they will make a salt and water. And when this happens, and it's in water, because acids and bases are generally in water, and you can visualize that you have like a coffee cup, and we'll do this, and you have water in there, and you dump these things in here in the HCl, and what happens? The temperature, we have a thermometer in here, and the temperature will change, and generally it's going to go up, and the temperature goes up. All right, so something happened here, and we have all this is in water. So what's the system? What's the surroundings? Well, you have to be careful here. What are you measuring the temperature change of? And when we reacted this stuff in water and we saw a temperature change, delta T, by the way, means temperature change, and we saw a temperature change of, say, 12 degrees Celsius, what was the system here? Well, the system is the sodium hydroxide and the hydrochloric acid reacting together. That's the system. What's the surroundings? Surroundings everything else. But here's the thing, and this is the point I'm trying to make here, is what did you measure? Did you measure the system or did you measure the surroundings? When you react sodium hydroxide with hydrochloric acid and water, did you measure the system or did you measure the surroundings? And what did you measure? You measured the surroundings. And you may say to yourself, well, what do you mean? How can it possibly be the surroundings? And so you look at this, what's reacting? The sodium hydroxide with the HCl. That's what's reacting. What's the water doing in here? The water is just so things can dissolve. It's kind of like when we did, those chapter 7 problems, not chapter 7, but those quiz or homework number 7s, or maybe it was lab number 7. It was number 7 something. Okay, and we did a bunch of stoichiometric solution reactions, and some of you emailed me and I said, well, the water's there just to get it to dissolve. It's not not part of the problem. Well, the same thing's here. The water is there so you can have something to hold the reactions as it's taking place, but it's not the system. The system is the reaction. Water is the surroundings. So when we measured the change in temperature here of 12 degrees Celsius, that was a change of the water, which was the surroundings. That was the surroundings. The water's the surroundings. We're going to do a lab, as a matter of fact, where we're going to measure temperature changes of solutions that we're going to mix together. And one of the important things is we have to keep straight. What are we actually measuring? Well, we're actually measuring the amount of energy released by the sodium hydroxide and the hydrochloric acid reacting together. Okay, that's what we're measuring. Okay, so why do we belabor the system versus surroundings? Well, here's the reason why. It comes down to sign. It comes down to the sign. We're going to have something called a sign convention. Okay, so all right, and a convention, when a sciencey sort of people get together, a convention, not just when we get together, because that's like a convention, like a no, a sign convention. A convention is where everybody agrees. We're all going to agree that we have to decide that things have to go either one way or the other. And as long as we all agree that things go one way or the other, then we'll all get the same answer at the end. Okay. Now, when we talk about the flow of energy, we have to decide whether it's which direction you're going. Is it positive or negative? And you may say to yourself, well, what does that matter? Well, it matters all the difference in the world, whether something is positive or negative when you put it in your calculator. And so if it's supposed to be negative and you put in positive in your calculator, if it's supposed to be positive, you put a negative in your calculator, well, you're going to not get the right answer. And ultimately, that's what we're really interested in, right? Is we want to get the right answer. So the convention is going to be from the standpoint of the system, or from the view of the system. All right, remember, this is always, and you got to keep this straight. It's always from the view of the system. This is why it's so important we figure out what's the system, what's the surroundings whenever we're trying to decide something. From the viewpoint of the system, if it's energy out, it's negative. And energy in, it's positive. All right. If energy's coming in, it's positive. You have it. Well, that makes sense because you're adding something. And so we will say that something is going to come in and we're going to call it energy. And if it comes in, we're going to increase the amount of energy that we have. And if it's negative, that means energy has to be coming out of the system because you're losing it. Okay. You're losing the energy. Now, how does this look? Now let's go back to our reaction that we just had, that we just did in a coffee cup, and we have all this water in here. All right, and I've already told you that the water is the surroundings. Let me get this in here, make it look just a little better. Whoops, there it goes. Okay, we have water and we're doing a reaction in water, and so we dump in some sodium hydroxide and HCl, and we have a thermometer in here. There's a thermometer. And we see the temperature goes up from here to there, and that's delta T. And let's say its delta T is 10.0 degrees Celsius. That's change in temperature. Change in temperature is starting temperature, finishing temperature. It's final minus initial. Okay, that's what delta means, is change. And we see there's a change in temperature when you dump the two in here. So I've already said that the sodium hydroxide plus the HCl go into sodium chloride plus water plus some heat, because that's what you're releasing here. Why else would the temperature of the water go up? This is what's happening. You're releasing heat when you react these things. And reactions usually either release heat or absorb heat. Now, the reaction itself is producing the heat. So, but where's the temperature? The temperature of the water. The temperature of the water goes up. So how can the temperature of the water go up? Well, the water would have to absorb the heat energy, but where's that heat energy coming from? It's coming from the reaction. So the reaction is the system. The water that it's taken place in is the surroundings. All right, which means that the reaction lost heat And so the energy change of the reaction is negative. The water, which was the surroundings, well, here, this should make sense at least for the water part. It had to gain heat. Why else would it increase in temperature? So the surroundings gained heat. And so the sign of the energy, when we talk about the reaction, if we talk about the energy coming out of the reaction, we have to say it's so many joules, but it's negative joules, because the reaction had to lose heat into the surrounding water. And if the water has to gain heat from the reaction, so as one gains, the other loses. Okay, so it's very important that we keep track of these systems. Now, what if we were to take solid, no water, sodium hydroxide, and HCl, and then react the two? Then if you have no water there, what'll happen is that the solid that you just mix together and the resulting products, they will go up in temperature as well. But in this case, it's still the system. It's still the system. The solid is still the system. But the surroundings would be like the container it's in or the air that's surrounding it or whatever. Okay, so it's still the system whether you mix it in water or not. It's just what gets hot. What gets hot? So what are you measuring? Okay, you got to be careful whatever you're measuring. So if I stick the thermometer into the solid sodium hydroxide and pour some HCl into it, and the temperature goes up, well, now I'm measuring the temperature change of the reaction itself. Whereas if I did it in water, I'm measuring the temperature change of the water, and we have to back out from that and say, well, you know what? The water was the surroundings. It's not the reaction itself. Okay. And this happens a lot. And so usually when you do a lot of these, you see that the water heats up and you say, oh yeah. That's energy being released by the reaction. That's what heats up the water. Okay. All right. So having done that, now when I say, the reaction releases heat or a reaction absorbs heat, or I say that the surroundings absorbed heat or the surroundings released heat, and we're going through all this trouble of that, and I say, well, we're released and absorbed energy, which is heat. What we're really saying is that we have the system has an energy. And we're going to give it, and this is one of the few things that's going to make sense in chemistry. Guess what the letter for energy is? It is E. Sure enough, E is energy. And so we say that there's two kinds of energy in this world. And we say that first off, we're going to say, and we'll go ahead and put the letters down. We're going to say Q plus W. And Q, we're going to say, is heat. And W, we're going to say, is work. And usually when we say work, we say pressure volume work. Pressure volume work, usually. All right. Now, the textbook, now here's the thing. Textbook goes into about, doing pressure volume work and calculating how much pressure volume work you've done and pressure volume work this and pressure volume work that. And I will tell you, it's good to go ahead and do some of the examples, but as chemists, we really don't care about pressure volume work, but we have to go through this to develop how everything's related. Okay. So we have heat and we have work. Now we have two different kinds of energy that can add together to get the total system energy, okay? And the total energy of a system we don't know, Well, what I'm going to say is we're going to have something called the change in energy, which is the energy between what we start and what we end with, is going to be however much energy you add or remove in the form of heat, and however much energy you add or remove in the form of work. Okay? E as a specific value, as opposed to the difference in energy, is very hard to find, very hard to determine. As an aside, okay, E is a specific value. Delta E, delta, by the way, means change. Okay, so the change in energy of a system is the heat plus the work. All right, now I made the statement over the right-hand side, and I said, E as a specific value is very hard to determine. And you may say to yourself, well, wait a minute now. I know how much energy something has. I mean, it's how fast something's going. Well, that's kinetic energy. This is true. This is true. How fast something is going, it has a certain amount of energy that's associated with it. But when we talk about the grand total of all sources of energy for something, we have to add up a lot more than just how fast some object is going. Look at it this way. We have energy, which is the sum of all the sources of energies. We might as well say total energy. Let me clean this up a little bit. Total energy is the source of all the possible energies: energy 1, energy 2, energy 3, blah 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 blah. And these things are like energy of motion. Okay, how fast is a thing going? Okay, but how about the energy of the individual electrons? How about the energy of the individual protons as they wiggle against each other? How about the electrostatic potential between the electrons and the protons? How about the nuclear binding energy? That's holding the atom together in the first place. How about the energy that's holding the different subatomic particles, like the different what are those things called? Quarks and such. And if you see what I'm getting at, is as you dig further and further down to the things that make up matter and motion and potential energy and all this, when you get down to it, it's actually pretty hard to figure out what the absolute energy is of anything. However, since the change in energy of anything is determined by the total of how much heat you add or remove, or how much work you add or remove, we can calculate the difference in energy, though, very easily. Very easily, in fact. All right. And so now I'm going to just throw this out here and say that delta E, the change in energy, is path independent as far as the total energy goes. Okay, in other words, E is a state function. Which means it's path independent. Okay, and the classic example for E being path independent is if you have like 3 containers containing water. Let's say you have water here, and you have an ice cube, and here you have solid ice, and here you have boiling water, and it's boiling away. All right, but it's the same amount of water. These are bubbles, by the way, and this is 100 degrees Celsius. This is 0 degrees Celsius, because ice water, if you have ice and water at the same time, it should be 0 degrees Celsius. And solid ice, let's say this is minus 100 degrees Celsius. Okay. The energy of this system right here does not matter whether you start with solid ice and melt it to get the ice cube in the water, or whether you take boiling water and cool it down. This energy is greater than that energy, and this energy is greater than that energy. But the energy here, if you have the same amount of ice and the same amount of water, and you prepare the system so it has a particular amount of water with a particular amount of ice, then it will have a defined amount of energy. Now, I don't know what that energy is precisely, but I do know to go from here to here takes a certain amount of energy. And to go from here to here also takes a certain amount of energy. To go between boiling to water with ice and go from ice, solid ice, to water with ice, it takes a certain amount of energy. I do know that, and I can measure that. I can measure the heat flow in between. But once I prepare that system, it has a particular energy, and that's what it means to be a state function. Here's another way of looking at state functions versus path-dependent functions. Let's say you're climbing a mountain. Okay, you start down at the bottom, and you're going up to the top. Okay, you can either go this way, or you can take around the mountain, climb up the mountain. You know, in other words, you don't climb up straight up the side, you take the road that circles the mountain. But after you're done, you're at the top. What's the change in energy? Well, the change in energy is from here to there. The path you took is the same amount of energy once you get up to the very top, from the bottom to the top. It's the same amount of energy whether you take the route going around the mountain or you go straight up the side. It still takes the same amount of energy. You're working against the force of gravity. You have a distance that you're moving against the force of gravity, and that's from the bottom to the top. Of course, we're assuming there's no friction losses or anything like that. So the path you take, it can be any path you want it to take, but the amount of energy it takes you get from here to there, regardless of the path, is the same. So that's what we mean by it's a state function. So your height, so the energy up here and the energy down here are what are called state functions. And so the difference between the two is delta E. Okay, so they're both state functions. Your position is a state function. How you got there is not a state function, it's path dependent. Okay, so we have heat and work. Now, getting back to the sign convention, which we started out with, we said, you know, if energy is going in, then we're going to say it's positive, and we're going to say if energy is going out, that it's negative. When we have to keep very straight as far as the sign convention. Okay, so we say energy out, we're going to say positive, and energy in, we're going to say negative, and we're going to give these special names, by the way. We're going to call this, when energy comes out, hold on, let me switch that around. Energy in, energy out. When energy goes in, we're going to call this endothermic. And when energy comes out, we're going to call this exothermic. Endo means in, exo means out, thermic means heat. Okay, so when its energy is positive, we're going to say it's out, we're going to say it's endothermic, we're going to say it's coming in, and when energy is negative, we're going to say it's coming out, and we're going to say that's exothermic. Okay, so how does this work in a problem? All that blah 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 just to get to this example right here. Okay, and so how does this work in a problem? So we say, what is the change in energy of a system that absorbs 14 joules of heat from the surroundings and does, let's say, 18 joules of work on the surroundings. All right, so we got to decide what's the change in energy of the system. Now, the key thing that we're looking at this problem here is we've got to say, well, we have heat going in one direction or the other, and we have work, and work's going on one direction or the other. Okay, and we got to decide what's the sign of each one. And so the relevant equation is energy is the heat, that's what Q is, plus W. All right. And so what's the heat? Well, this is the heat, this is Q. And what's the work? Well, that's W, that's work. And we've got 14 joules, we have 18 joules, and we have to decide. Now, this is where we have to be very careful. It all comes down to the sign. Okay, so remember, this is always from the view of the system. All right, now what does that mean? Well, if the system is losing heat, then the surroundings must be gaining. If the system is gaining, then the surroundings must be losing. The wording makes all the difference in the world. So we say a system, so we see over here, we have to look at this. We say a system absorbs 14 joules. The system absorbs 14 joules. That means energy is going into the system. So the sign for that 14 joules must be positive because it's a system absorbs. And then it says, and does from the surroundings, and does, and from the English, the plain English reading of this is the system does. Okay, and the system does 187 of work on the surroundings, which means you are doing work from the system, which means you're going from the system with work, means this must be minus 18. That must be negative. Because where does the energy come from to do the work on the surroundings? It had to come from the system. If you're coming from the system, you're negative. If you're absorbing heat from the surroundings, where's it going? It's going into the system. If you're going into the system, it has to be positive. And so we can actually write this down now, and we say, well, the change in energy of the system is the 14 joules, and I'm going to put a plus here just to be consistent, and then we're going to say minus 18 joules of work, and the total change is minus 4 joules. That's the change in energy of the system, is minus 4 joules. So the system, if it absorbs 14 joules and does 18 joules of work on the surroundings, the net change in energy is minus 4 joules. Minus 4 joules. Okay, let's do another one here. Let me go ahead and pull up another slide. All right, so how about make this a little bit surroundings. Okay, so the system loses 12 joules and the surroundings do 10 joules of work on the system. Okay, so now in this case, the system loses. So I'm looking here and I say system loses. That must be minus. And then I say the surroundings do work. Now, if the surroundings were doing work, that means that the surroundings lost energy because the surroundings are the ones doing the work. So what's it doing work on? It's doing work on the system. So this is once again plus. So this is 12. This is minus 12 for losing the heat, plus 10 joules for the surroundings doing work on the system. So the system lost heat, 12 joules, that's minus. The surroundings did work. Surroundings have lost energy because the surroundings are doing the work. But what's it doing work on? It's doing work on the system. And so that becomes plus 10 joules. And once again, we get minus 2 joules. It just worked out that way. Okay. And that is delta E of the system. Okay. And that's really all you can do with this delta E equals Q plus W. All right. But this is always assuming, that the work is some sort of pressure volume work. Okay. It's always some sort of pressure volume work. All right. It is 10:53. This is a good place to take a break because we're going to jump into something that's going to be a little different from this, but derived on what we're doing. So what we're going to do is take a 7-minute break and we'll go to 11 o'clock. Okay, so we're going to take a break to 11 o'clock. So let me put down here, break to 11 a.m. and we're going to continue. Okay, and what we're doing next, matter of fact, I'm going to put here, next will be something called delta H. Okay, just to give you an idea what's going on here. So let me stop recording. Recording, stop.